Okay, so sorry about that little interruption. Got chased out of the room, but I've relocated to a new room, which I think we're probably safe in. Okay, so, pardon me. What I had been talking about was the current that flows as the capacitor discharges. Remember what we did was we originally charged the capacitor, and then once the capacitor was fully charged, we removed the battery from the circuit, attached the now fully energized capacitor to only the light bulb, and at that point the charge in the capacitor begins to rebalance, so that the positive, the excess positive in the top plate flows around to repopulate the negatively charged bottom plate, so the charge balance returns back to equality. But that implies that a current is flowing through our light bulb, or whatever our resistive device is, let's say a light bulb, in which case the light bulb lights, and we see the evidence of the current flow in the amount of light that's coming out. The light that is coming out is in fact related to the power output, because after all, light is a form of energy. Energy is being put out per second. That's what power is, energy released per second. And so the Joule heating law then applies. And so the Joule heating law P equals I squared R. As the current flows, there's power. But as we've discussed, the current decreases with time. And therefore the power output decreases with time, which is just a mathematical way of saying the bulb gets dimmer as time goes on. Okay, and then I said without much justification, in fact, really without any justification, that the mathematical function that describes the physical behavior of the light bulb is this thing here. And the crucial feature of it is this thing here, the exponential function, which presumptively you have seen somewhere before. And you remember that if you graph an exponential function, the graph looks approximately like that, okay? And so I want to talk about a couple of things, but I think what I will do is discuss what I want to discuss in the form of an example. So let's see. All right, so let's plot this function This circuit is known reasonably enough as an RC circuit, resistor capacitor circuit. No potential here, no V or EMF, because we took the battery out of the circuit. Okay, and so suppose our values are, we have a resistor that's 100 ohms. I neglected to mention when I was telling you about resistance that in fact you can artificially construct a resistor device. In fact, let me pause the recording and go get one. Okay, so I have a couple of buckets of resistors here. And superficially, so this one here, this bucket is a bunch of resistors who have resistance of 68 ohms. This is what a resistor looks like. Those colored stripes on there that maybe you can see and maybe you can't are actually, if you know how to read them, they actually will tell you the resistance that this thing is designed to have. These are actually designed to have a given amount of resistance. Okay, they're manufactured at a company that says, we want to make a resistor that is 68 ohms. And that's what a 68 ohm resistor looks like. Okay, this is what a 100 ohm resistor looks like. And I think you'll agree The two things look a lot alike superficially. The color stripes are different, but this is 100 ohms. This is 68 ohms. Okay. But anyway, this is what a resistor looks like, an artificial one. And these things are built into all sorts of circuits. And you want to artificially increase your resistance or sometimes artificially decrease the resistance, and you use these sort of things to do so. Now, why you would want to do so, we'll talk about another time. But that's what a resistor looks like. And so when I talk about a 100 ohm resistor, that's what I'm talking about. And by the way, the other lecture, in one of the previous recordings, I mentioned when I was talking about resistivity, I mentioned nichrome. This is a spool of nichrome wire. Okay? Superficially, it just looks like any other metal, but it is, in fact, comparatively high resistance. Compared to what? Compared to copper. Compared to wood, this has very little resistance, but compared to copper, this is a lousy resistor. This is what you use to make toasters, or at least toaster elements. Okay, so anyway, and then capacitors, you know about capacitors. So suppose that we have a capacitor whose capacitance is pretty big, but 0.1 farads, okay, a tenth of a farad, right? And suppose we charge this thing up with a couple of D-cell batteries, so 3 volts. And so this is exactly the sort of circuit you could build right, in your lab, right? A couple of D-cell batteries, one of the resistors that I just waved at you, 100 ohms, tenth of a farad capacitor. We can do that. So what do we get? Well, okay, so we want to plot this function. Okay, the function that we want to plot is the general form of it. I'll just repeat it here. Okay, let's take a quick look at this. In this expression, bring it a little closer here. In this expression, R there, that's the resistance of the circuit, and in this particular case, essentially all of the resistance of the circuit is in this resistor object. Okay? The other wires that you use to connect the resistor and the capacitor together, their resistance is negligible compared to this. Okay? Remember that we actually calculated the resistance of an alligator clip wire in a previous lecture, and it was 0.001 ohms, right? So this is huge compared to that. So we tend to ignore the resistance of the wire in favor of just this. Okay. C is this capacitance here. T is, our variable. And then I naught, okay, now I naught is interesting here and important. I naught is the initial current that flows. Okay, now here's how to think about this. If we had, now we're going back to charging the capacitor. So let's go back to charging the capacitor. Now, if I didn't have the capacitor, in other words, if I just had a light bulb and no resistor and just plugged it in, well, you know what would happen. I'm sorry, this is meant to be a battery. So this is my 3 volts, and this is my 100 ohm resistor. So then the question, if I did this, I could ask the question, how much current would flow when I hook this up? Well, we know the answer to that. We did that in the previous recording. The answer is given to us by Ohm's law. Specifically, the current that flows would be V over R, or EMF over R, depending which one you're in the mood to use. And so our potential difference here is 3 volts. Our resistance is 100 ohms. And so the current that we get is going to be 0.03 amps. Oops, I'm sorry, mistake. I'm going to be consistent with that. That should have been just 10 ohms, I'm sorry. Okay. 10 ohms. I'm doing well with this recording. So 0.3 amps. Okay, that's better. That actually makes more sense. Okay, so we 3 volts, just 10 ohms of resistance, and we'll get a current of 0.3 of an amp, which is still a respectable current, by the way. It's certainly enough to light a light bulb. And so, yeah, this light bulb would light, and that's fine. However, this is, of course, not the circuit that we have. What we really have, of course, is we have a capacitor in here. And so we're not going to get this current except at one instant. We will get this current at the instant we first close the switch, the instant we first connect the alligator clips, the instant we first close the switch, the current starts to slow, and at that very first instant, the very first current that flows will be, in fact, this amount. Now, the current will drop immediately from this value, but it will start at this value. And in fact, what I have just calculated is actually the initial current, okay, which I actually will get that from this expression as well, because, so I of t, let me actually plug in these numbers. Okay, so my capacitance is 0.1 farad. I'll put that in. So C equals R equals B equals. Okay, so I naught is the potential difference divided by the resistance of the circuit times e to the minus t over RC. But the initial current, of course, happens at t equals 0. That's what initial means, t equals 0. Then at t equals 0, we have I at t equals 0. So we'll just substitute t equals 0 over here. So we have V over R times e to the minus 0 over, and then I can put in RC, but I'm not going to just yet. Okay, because look what happens here. E to this thing, this exponent becomes 0, and raising anything to the 0th power is equal to 1. Not 0, 1. Okay, so this whole thing here evaluates to just 1, because anything to the 0th power is 1. And so our current at t equals 0, which I'm going to give the symbol I sub 0, is then simply equal to V over R, which we just calculated. And so that's going to be, as I just did, 3 volts over 10 ohms, 0.3 amps. Okay? So now I have the value for I sub 0 for this function. So if I want to, I could do this. Now I'm doing this in unnecessarily slow motion, but I'm trying to get you comfortable with these ideas. So my function, after having accomplished this, I can write my function in this form here. Okay, I just draw your attention to it here. Okay, now I'm not done, but that's my second step. Now what I'm going to do is I'm going to replace the symbols R and C with their actual values. Okay, well, I'll do it simpler. R is equal to 10 ohms. C is equal to 0.1 farad. And so this gives you 10 times 0.1 is just 1 ohm farad. Now, ohm farad is not at all obvious what in the world that is. Okay, so let me show you what it is. An ohm farad, I mean, we could just live with it. We just write it ohm farad, but let me not. Let's check out the units of ohm farads. Okay, well, let's see. Well, an ohm is defined as a volt per amp. That's from Ohm's law. And a farad from Q equals C times V. A farad is a coulomb per volt. So the product of ohm with farad is simply volts per amps times coulomb times volt. Okay. So the volts divide out, which leaves us with coulombs per amperes. But an ampere is a coulomb per second. So if I combine this and this together, I get, so coulomb per amp, so I get a coulomb per amp is a coulomb per second. The coulombs divide out, and I'm left with 1 over seconds, which is just seconds. In short, the units of R times C is just seconds. All right. So this is, here I mean units of, and then these are the actual units, and you multiply it out and you get seconds. Okay, well that's interesting. Well, it is interesting. In fact, it's not only interesting, it's crucial. But I'm not going to tell you why it's crucial until the next lecture.